Having established that the aldol is a reversible reaction and that there's equilibrium involved, we now need to consider the retro aldol, the reverse aldol reaction, in a little bit more detail. So first, an overview of the reaction, starting with the product, the aldol product of a ketone. When treated with sodium hydroxide, that can go back to 2 molecules of acetone. So as we already discussed in the previous lesson, for the ketone, this is actually going to favor the ketone starting materials, which are the products of the retro aldol. So let's look at the mechanism of the retro aldol. Step 1 is going to be deprotonation of the OH alcohol with sodium hydroxide. These bases, the base on the left side, which would be OH minus, the base on the right side, which would be OR minus, are similar in strength. So this is going to be an equilibrium process, and again, it's going to have an equilibrium constant of close to 1. Step 2 then is the expulsion of the enolate as the leaving group, generating a CO pi bond. Okay, so this is very similar to the mechanisms that you have seen with regard to acyl transfer, in which we generate a CO pi bond in the second step and kick off something that could contain a leaving group. We don't usually think of a carbon as being a reasonable leaving group. The only reason it is in this case is because the minus charge is being put onto a carbon that's alpha to a carbonyl, and it's an enolate, and we've already talked about why enolates are more stable. So this step is actually, both of these first 2 steps are similar to the mechanism of hemiacetal hydrolysis that you have already seen, in that you first deprotonate and then generate the carbonyl and kick something off as the leaving group. The enolate is a slightly worse leaving group than OR minus. It's a slightly stronger base, but again, this reaction is taking place under basic conditions, so it's still a reasonable leaving group. Not a great one, but it is a reasonable leaving group. And then finally, in step 3, the enolate gets protonated with water. Okay, we made a molecule of water earlier as we were using OH minus as a base. So now we use that water to protonate the enolate to give back the ketone product. This will be a favorable step with respect to pKa's. We're taking something with a pKa of 19 and forming something with a pKa of 15.7. Conjugate acid pKa of 15.7. So the favorable acid-base reaction in step 3 is going to drive step 2 because we are forming a weaker base. I know it's a little weird to think of OH minus as being a weaker base, but in this particular reaction it is. Okay, so that's the retro aldol as it takes place under laboratory conditions. A retro aldol takes place every time you break down a molecule of sugar in the digestion of your food. So step 4 of glycolysis, remember glycolysis is 10 steps through which you take glucose and convert it into 2 molecules of pyruvate. Glucose is a 6-carbon molecule, pyruvate is a 3-carbon molecule, so somewhere in the middle of that you have to break this 6-carbon molecule into 2 3-carbon molecules. And the reaction that does that is a retro aldol reaction. So specifically, fructose 1,6-bisphosphate is the substrate for this reaction, and it gets broken apart, breaking the carbon-carbon bond into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. We're not going to cover the detailed mechanism of this reaction right now. We will in a future lesson when we talk about enzymatic mechanisms, but this requires an enzyme that is called aldolase because it catalyzes an aldol, or in this case, a retroaldol reaction. What you should note is that when plants carry out photosynthesis or animals carry out gluconeogenesis to make glucose out of smaller building blocks, they are actually carrying this aldol reaction out in the forward direction, building up a 6-carbon molecule from 2 3-carbon building blocks. But for now, I just want you to look at these structures, and if you look at the ketone piece that's in orange and the beta hydroxy piece that's in green, you can see that beta hydroxy ketone being broken up, and what was the OH of the hydroxy now becomes this C double bond O of an aldehyde. And the bond that's being broken is the alpha beta bond with respect to the beige ketone. Okay, so this is a more complicated example because it's a biologically relevant molecule, but it's really only complicated in that you have the phosphates sitting there. Well, they just sit there in the beginning and sit there at the end. They don't get involved. And there's also some extra OH groups that are a little closer to the action of where the reaction takes place. But as you can see, the extra OH groups, such as the one on the alpha carbon to the ketone in the starting material, this OH is just carried through the reaction and does not actually get involved in the mechanism. Okay, so there's the retroaldol for you.